Today we're going to take a look at the second part of chapter 2, and that means we're still looking at water and aqueous solutions, but we're going to pick up where we left off and start to explore weak acids and bases and the way they behave in water, as well as how buffers work, why it's important that we have them, and then how water is going to participate in some biochemical reactions. And so we're going to lead off with a recap of talking about really the entropic way that water orders itself. And so if you recall from the last time we talked, we looked at nonpolar molecules, so molecules where there isn't a significant difference in electronegativity and the electrons are shared equally, as opposed to water, which is polar, where there is a difference in electronegativity between the oxygen and the hydrogen. And so the difference between a non-polar compound and a polar compound can actually be seen here, where we have the tail of a lipid, and you can actually see the way that water is organizing itself around that non-polar molecule. Now, it's important that we note that depending upon the type of non-polar molecule, say, for example, if we're looking at a cluster of lipid molecules, it's really the edges of that cluster that force the ordering of the water. And in between, so for example, in between those two nonpolar molecules, that area is still going to be very hydrophobic. Whereas if we were to look at a micelle, all of the hydrophobic groups are actually sequestered from the ordered shell of water molecules outside of it. And because of that, there actually isn't nearly as much of the shell itself that's created. And so in both of those cases, we see that our entropy is increased. And you might be wondering why. And part of that is, well, the bulk water is going to have very little order. And so that means it's going to have relatively high entropy. Whereas water that is near something that's hydrophobic is going to be highly ordered, and so that's going to have lower entropy. And so that is in part tied to the number of water molecules that we have available. And so when we're thinking about this in like a broader picture, it's really low entropy that's going to be thermodynamically unfavorable. And so it's because of that reason that we actually see something that's hydrophobic having low solubility. So we're going to bridge from there and talk about some of the other effects that solutes are going to have on the properties of water. So if I were to take water and put something in that water, how does that change the behavior of the solution? So if we think about colligative properties, those are properties that don't really depend on what the solute is, just what the concentration of that solute is. And so those are things like boiling point, melting point, and osmolarity. Non-colligative properties are dependent upon the actual identity or the chemical nature of the solute. So these would be things like viscosity or surface tension, taste, color, and obviously other chemical properties, say for example like reactivity. And so when we're thinking about this, right, in terms of a cell, we know that cells are highly concentrated solutions and they're going to have osmotic pressure. So it might be useful for us to be able to take a look at what some of these terms are and have working definitions for them. So osmolarity is the concentration of a solution that's expressed as the total number of solute particles per liter. So that's an osmole per liter. Another way of saying that is that an osmole is 1 mole of particles. Doesn't matter what the particles are, just 1 mole of particles that contribute to the osmotic pressure of a solution. And we're going to contrast that with molarity. You've studied molarity in earlier chemistry courses. And the idea here is that the number of molecules of each solute per unit of volume is expressed in moles per liter. So here we're differentiating between types of solutes. So if I wanted to give you an example, then let's take a look at sodium chloride. Sodium chloride is going to dissociate completely because it's an ionic solid in water, and it's going to form sodium plus cations and chloride negative anions. Thus, for each single mole of sodium chloride in solution, that becomes 2 moles of particles. And so 1 mole of Na plus and 1 mole of Cl minus. So one way to think of that is if I have a solution that's 1 molar NaCl, it's going to have an osmolarity of 2 osmoles per liter. By comparison, if I take a look at something like calcium chloride, So a solution of 1 mole CaCl2 is going to have an osmolarity of 3 osmol per liter because 1 Ca2+ ion is generated as well as 2 chloride ions. Now what if it's a 1 mole per liter solution of glucose? Well, it's going to have an osmolarity of 1 because glucose doesn't dissociate, so it doesn't create any more particles than existed when you first put the glucose into solution. Now, those concepts are important when we start to think about the effect of extracellular osmolarity. So that's a fancy way of saying when we think about the concentration of solutes outside the cell. So whether you're thinking about something like IV fluid or how you might transport, say, for example, an organ, or if you're thinking about how you might prep cells, you care about what the concentration of the solution that you're putting those materials in or taking them out of because of the way it's going to change the net movement of water. And so if we think about the concentration of solutes inside the cell being greater, that's what we would refer to as a hypotonic solution. If it's equilibrated, so if the rate of water going in and the rate of water going out of the cell is equilibrated, then that's going to be isotonic. And if the outside is greater, then it's going to be hypertonic. And so ideally, if we're thinking about biological systems, we want our net movement to be constant. That's good for a patient or a cell culture. If our system becomes hypertonic, then that's where water leaves. Our cell can become crenated or shrink, and that can actually cause damage. Or if it's hypotonic, that's also not good because the water is going to rush in, and it can actually, as it swells, cause the cell to burst. And so if you think about something like the concentration of what's within a cell, right, it would be reasonable for it to be 0.3 osmol. So in that case, right, we want anything that is going to be a concentration outside of that cell to also be 0.3 osmoles. And so that would suggest that we care a lot about what the identity of the solutes are. So is it something that when it dissolves, it creates 2 particles or 3 particles or only 1 particle if it solubilizes? So these are questions that we always want to think about when we're preparing solutions and when we're using solutions. And part of the reason why that's important is when we think about, right, the actual concentration itself, we can predict what's going to occur. So say, for example, if, right, my concentration is the same, right, inside and outside of the cell, then there's going to be a net flow that is the same. It'll be equilibrated. If, however, right, my concentration outside is less than what's inside, then I'm going to see, right, a net flow of water going in. Right? If what's inside is less than what's outside in terms of concentration, then I'm going to see a net flow of water out. And you should be able, regardless of the circumstances in terms of what the solute is or what the concentration is, you should be able to predict that, right, based on your understanding of whether something's going to be hypotonic or hypertonic or isotonic. One of the other properties that we need to pay attention to in terms of water is the fact that it ionizes. So concentrations of something that is participating in an equilibrium process aren't independent. In fact, they're related via our equilibrium constant. And so that's just saying that the rate of exchange from water to H plus and OH minus, right, is dependent upon this K equilibrium expression. And we know that KEQ can be determined experimentally for water, and we actually know that the concentration of water can be determined from its density. And so when we're looking at something like the ionic product of water, we know that Kw is the equilibrium constant specific for water. And so we can write that based on the concentration of H plus and the concentration of OH minus, or the K equilibrium times the concentration of water itself. So in pure water, our concentration of H plus and our concentration of OH minus should be equal. It should be approximately 10 to the negative 7. Multiply those together, that's going to give you a Kw of 1 times 10 to the negative 14th. Now, why Why do we care about the concentration of H plus and OH minus? Well, we care about it because of the expression pH is equal to the negative log of H plus. So that's a mathematical expression, but what it's relating is a logarithmic scale to the concentration of H plus. And so we know that the pH and pOH always add together to be 14, and we know that in a neutral solution the pH is 7, so we can actually then calculate what pH is going to be using this expression. Now it's really important that we clarify that while it's common when pH is taught, that it is taught on a scale of 0 to 14, but in reality, pH can be negative. In fact, there are some species that are significantly negative in terms of their pH. So if we take a look then at our pH scale, one of the things that is important for you to understand is that you can actually, if you know the H plus concentration or you know the pH, you can go back and forth between the two. So if I told you that the pH was 5, you should know that the H plus concentration is going to be 10 to the negative 5th. And that's really useful if you have to estimate, right, or anticipate whether or not the answer to a problem that you're solving is reasonable. At least it gives you a base to work from. Now, if we take a look at strong acids, we know that those are going to dissociate completely. That means that HCl, right, is going to, in solution, become H plus and Cl minus completely. It's going to dissociate so that there's no HCl left, there's only the two ions. But what about weak electrolytes? So if we look at a weak acid, say for example acetic acid, what we're going to find is that the K equilibrium expression is such that there's not complete dissociation of the acetic acid. In fact, it tends to stay mostly as CH3COOH, and very little of it goes on to form H plus and CH3COO minus. But we can calculate that equilibrium constant, and then we can use that equilibrium constant to be able to determine our concentration of H plus. Now, if you're thinking about that from an example standpoint, right, let's look at the following. So what is the final pH of a solution when 0.1 moles of acetic acid is added to water to a final volume of 1 liter? And so you can do the equivalent of an ice table, which you've probably done in general chemistry, but you also can just simply think of it in terms of concentrations. You have your K equilibrium expression, and you know what your change is, right, which we represent by the variable x. And so then you can go through and you can actually solve using a quadratic expression. That gets tedious and it can be a bit of a headache. So we can actually approximate it and get fairly close, right, as long as our change, right, the change in x, is relatively small compared to our concentration that we began with. And so in this case, we eliminate that minus x term down here that we used previously. And so now we can just calculate it in terms of x, and you'll notice the pH that we calculated using our simplification was 2.88. If we go back up, right, it's 2.883 as opposed to 2.880. So it's a pretty reasonable approximation, and it works well for weak acids and bases. You always want to ensure, though, that x is significantly less than the concentration of the total acid. The guiding principle there should be about 5%. Now, it's not just Ka that's valuable to us, but it's also pKa. So pKa is, again, a logarithmic scale. And we use pKa to be able to determine whether an acid is strong or weak. If it's a strong acid, it's going to have a large Ka, and that means that it's going to have a small pKa. So if you're comparing two acids, the smaller the pKa, the stronger the acid. Likewise, if you're comparing two Kas, the larger the Ka, the stronger the acid. And so if we look at a couple of examples here, we have monoprotic acids like acetic acid. That has a pKa of 4.76. And so we know that's a relatively weak acid, right? Especially if we compare it to, say, H3PO4, right? The first of its pKa's, which is 2.14. Notice, because it's a polyprotic acid, it can actually give up more than one hydrogen. This pKa, right, of 6.86 is for the exchange back and forth between H2PO4 and HPO42 minus, right? And then the third pKa. And so one of the things that you'll notice is that as we start to talk about pKa, you can actually predict the chemical reactivity of these molecules by looking at their equilibrium constants or the logarithmic value of that equilibrium constant, the pKa. And those dissociation reactions are going to be highly useful when we start to think about our next topic, which is buffers. So buffers resist change in pH. A weak acid and a conjugate base are typically what are used to form a buffer. And so at pH equal to pKa, there's going to be a 50-50 mixture of our acid and the anion forms of the compound. And because of that, that means that our buffering capacity of any acid anion system is always going to be greatest when pH is equal to pKa. And we lose, right, our buffering capacity when the pH starts to differ from the pKa by more than about 1 pH unit. Now that's important for us to think about as a concept because we're going to be selective in terms of what we choose for buffers. So for example, if I were to choose acetic acid and acetate as my buffer system, there are a couple of pieces of information that I would want to pay attention to. I know that the pKa is going to be 4.76. And so that means that if, say, for example, I were to add, right, a base into my acetic acid acetate, that base is going to take the proton away from my acetic acid and form more of the acetate. Likewise, if I were to add acid, that acid is going to react with the acetate to generate more acetic acid. And so you can see how the equilibrium will shift depending upon the relative concentrations you have of H+, Ac-, and your acetic acid itself. Now, if we look at that from a titration standpoint, one of the things that we'll notice are a couple of features highlighted in this graph. So the first is that if we were to start just with acetic acid, we would start with a relatively low pH. And as our pH approaches the pKa of 4.76, this is the point at which 50% of our acetic acid has formed our acetate. And if we were to continue adding base, in this case OH-, right, eventually we would have consumed all of our acetic acid, which means at that point in time we only have acetate remaining. Now you can see, right, where the slope of the graph, right, is significantly shallower. And so because that slope is shallow, right, that's one of the indicators that this is actually our buffering region. And right, we know that that should be plus or minus 1 off of our pKa, which in fact it is. So somewhere between a pH of 3.76 and 5.76 is the most effective buffering region for acetic acid. Now, since acids have different equilibrium constants, it would make sense that they also have different pKa's. So for example, depending upon the system that you're looking to buffer, you might choose acetic acid as your buffer for a pKa of 4.76, or maybe the phosphate buffer for a pKa of 6.86, or maybe the ammonium, right, with a pKa of 9.25. So really it depends on where you need your buffering region to be. Does it need to be between 3 and 5, between 5 and 7, between 8 and 10? And so that's something that as you start to think about problems will be key as you're selecting the components to make up your buffer system. Something that we need to talk about just a little bit is that if you're 1 pH unit above pKa, then your acetate concentration is going to, say, for example, be 10 times that of your acetic acid. If you are 1 pH unit that's below pKa, though, then your acetic acid concentration is going to be 10 times that of your acetate. And so it's really between these regions that we actually see our buffer. Now, when we're talking about buffers, and we think about them in terms of weak acids or bases that have a pKa that's near the desired pH, as the pKa is the inflection point of our titration curve, relatively large amounts of H+ or OH- ions can be tolerated without changing the pH. And so if, say, for example, we were to think about practical applications of this, right, there are a couple that come to mind. So the first is if we were to think about the intracellular pH of cells. So all reactions tend to have an optimum pH. And that's true because these are enzymes and they function in a highly specific environment. The solubility of polar molecules is something that can depend upon whether or not there's hydrogen bonding that's occurring. And then the equilibrium between carbon dioxide gas and bicarbonate is also something that depends on pH. And this is particularly key for blood plasma because bicarbonate as a buffer, even though the pK is 3.9, because of the presence of carbonic anhydrase, it can catalyze the formation of carbonic acid and maintain equilibrium between the carbonic acid and the dissolved CO2. But there are other examples. So the phosphate, right, typically has a concentration in the millimolar range. We talked briefly about the bicarbonate, but histidine is also an efficient buffer at neutral pH. And then there are other buffer systems that are found in vitro based on sulfonic acids of cyclic amines. So heaps and pipes and chase are all examples of other types of buffer systems. And when we think then about blood pH, say for example, we're going to look next time at acidosis and alkalosis, and we're going to talk about the physiological causes of that. But we're actually going to think about homeostasis with buffers, what disrupts equilibrium and what returns equilibrium. And so the next section will be some problems associated with the content that we've covered so far. Thanks again. Have a great day.